Models are how we forecast floods, droughts, and wildfires. They help us design experiments and test new hypotheses. They can provide a strong control for Earth system's processes that are really difficult to describe. Community models represent the combined investment of millions of hours of research by thousands of scientists across the world. Models are incredibly important to science, so what exactly are they? There are basically two types of environmental models that come from very different backgrounds. Physically based or process-based models use laws like the equations of motion or thermodynamics to develop a series of equations that are physically consistent with the real world. Physically based models make accurate predictions by leveraging the combined knowledge from hundreds of years of science history. They tend to be consistent and are useful for extrapolating through space and time. On the other side of things, statistical models mine datasets to find new or previously unstudied relationships. They're merely shapes that we give to equations that represent what we observe, without any direct ties to physical or thermodynamic laws. Because statistical models ignore science history, they can actually be incredibly fast, efficient, and even break new ground in science. Let's start with a trivial case of a ball bouncing across a rigid surface. We'll build two competing models, one physically based and one statistical. We can derive a physically based model for the motion of the ball using Newton's laws. We know that the only force acting on this ball is the force of gravity directly down, so it's got a gravitational acceleration of negative 9.81 meters per second squared. We know that acceleration is the first derivative of velocity, so if we integrate acceleration with respect to time, we get an equation for the velocity of the ball in the y direction as a function of time. We also know that acceleration is the second derivative of position, so if we integrate velocity with respect to time, we get an equation that tells us the y position of the ball as a function of time. As the ball's approaching the ground, it's coming in with some initial velocity. It strikes the ground, it probably deforms a little bit, and then it rebounds with some second velocity or exit velocity, v2. The ratio of the exit to the entrance velocity is the coefficient of restitution. Now let's take a purely statistical view of this. Let's say we observed the ball several times right when it started moving. It kind of looks a little bit like a line. So why don't we just fit the simplest statistical model possible, which would be a linear regression. The statistical and physically based model equations are pretty different from each other. If we plot them against each other, we can see that the solutions generally agree at the very beginning, where we had the data to build the statistical model. But once we enter the area where we didn't have data, they diverge. The statistical model doesn't pick up the effect of gravity at all. Now we've got a little bit more data how the system works, so we can build a more complicated statistical model. This one captures the same form as the physically based model, which is good, but it didn't get any information on what happens when the ball strikes the ground, so the rebound effect is missing. A purely statistical approach is trying to derive everything again from a limited data set. But why start there? As scientists and engineers, we've got this wealth of prior knowledge about the physical world. Why not build our models from that perspective? Let's try to come up with a model that turns rainfall into stream flow. It would be near impossible to use Newton's laws to try and simulate the impact of every raindrop with the soil, or off of every leaf or off of every sidewalk. So a completely physically based representation of rainfall runoff is just not possible. What we do know is that water is conserved. So some water is going to get caught up in trees, some of it's going to get stored in the landscape, and some of it's ultimately going to become stream flow. So let's start there. So the curve number says that every watershed has some amount of water that it can store. And we're going to estimate that using this equation. 1,000 divided by some value called the curve number minus 10. We're then going to estimate an initial abstraction, which is the amount of rain that got caught up in the landscape and didn't make its way to the stream. We're going to say that's 0.05 times the storage. We can then estimate the water that ended up in the stream as the amount of rainfall minus the initial abstraction squared divided by the amount of rainfall minus the initial abstraction plus the total storage. So there's a process-based understanding of the system here. We're understanding that some rain is going to get abstracted by the landscape, but it's not really physically based. This doesn't tie back to Newton's laws. So we would call this a process-based model. This is different from a purely statistical model because there's some acknowledgement of what is going on in the hydrological processes. Let's take a purely statistical approach now. We're just going to observe some rainfall and we're going to observe the runoff that ends up in the stream. And maybe our data points look something like this. With more rain, there's more stream flow, and we can fit a model to those data. So we'll assume that this is a linear model. In both the curve number approach and the statistical approach, there's parameters that we need to estimate from the data. To do this model intercomparison, we collect some publicly available stream flow and precipitation data from USGS and NCDC. We can see that the two models performed about the same. It's kind of a tie. The reason for this is that the curve number was a single parameter model that wasn't that different from linear regression. And the data are really noisy. There's probably more processes occurring that we didn't account for in either model. There's probably also just errors in these data sets. So what's the path forward, simplicity or complexity? Let's look at another case. The soil-plant-air continuum is used in Earth systems models to determine how water moves from soils into plants and up into the atmosphere. SPAC forms the basis of the water cycle in terrestrial biosphere models that forecast how the Earth is changing. This is a physically based model represented by a series of 4 equations that are all physically consistent with Newton's laws of motion, conservation of mass, and conservation of energy. The problem is this series of equations contains no less than 11 parameters describing soil textures, resistances to water flow, and plant physiology that are not easily determined. To estimate these parameters, we either need massive quantities of empirical data collected from forests, or we need very accurate guesses. Earth systems models leveraging physical relationships often run into this problem of too many parameters, which we call dimensionality. It's not to say that we can't proceed, but if you're taking this path in science like I do, be prepared to spend 2 to 4 years and $500,000 to reach a place where you can make accurate forecasts. It might then be simpler to model the soil-plant-air continuum with statistical relationships. But these models are immediately limited to interpolation only, which probably doesn't serve science all that well when our goal is often to study how the Earth is changing.